Okay, welcome back, everyone. My channel now has a name. It's called Your Helping Hand, and I'm Ansar, your helping hand. Hope you see what I did there. So today we're going to be talking about sampling distributions of normally distributed data, also known as sampling distributions related to normally distributed data or related to the normal distribution. Specifically, we're going to be talking about the sample mean and the sample variance, and then the other two sampling distributions will be in a different video. So before we get started, I just want to quickly reiterate some of the main points from the previous video, which was about the reasoning or the goal for statistical inference. So basically, the ultimate goal or the end goal of statistical inference is essentially we want to be able to get feedback on our models, we want to get feedback on our random variables and their parameters, and basically the assumptions that we put into those models and random variables. And the way we do that is by using our sampling distributions as well as statistical techniques to basically make inferences and say whether our assumptions were good or bad. So the most important thing with sampling distributions is that essentially sampling distributions are the distributions of a particular statistic of our data. And the reason we need sampling distributions is because those distributions, the sampling distributions, they give us the probabilities of particular outcomes for our statistics. So, for instance, for the sample mean, we'll have a particular sampling distribution, and that will tell us the probability of seeing our sample mean being a certain value or lying between a particular value. Okay, so the reason we go through this chapter about the normal distribution, or why we use the normal, there's a couple of reasons. So the first one is that in nature, in real life, in the physical world, there are many different phenomena that actually do have normal distributions that look like a normal distribution when you plot the histogram or the relative frequency distribution, which is the things that we were doing in the first week of term one with descriptive statistics. So that's the first reason. The second reason is that there's this theorem in statistics called the central limit theorem, which we'll kind of talk about later. But essentially, the CLT or the central limit theorem says that any distribution that satisfies a particular criteria or any random variables that satisfy a particular criteria, that when you take a sample mean of that data or of the observations of those random variables, that the sample mean of that data, no matter what kind of distribution the actual data has, when you take the sample mean, that the sample means distribution or the sample means sampling distribution is distributed according to a normal distribution. So essentially, what that means is that by studying the normal distribution, you can also use all of the information or all of the tools and techniques and results that we get from this chapter to study data that's not normally distributed. And we'll do that later on. Okay, then there's this other thing that you honestly don't really need to know. I'm just including it because I think it's quite an interesting fact. So there's this field in, I don't know if it's applied maths or maths, but it's called information theory. And basically, information theory is about encoding and decoding information from data. And there's this concept in information theory called entropy, and entropy is essentially a measure of information, right? So it's how much information is in a particular data set or in a particular kind of random variable. They don't really work with random variables, but that's besides the point. Anyway, so information theory says that if I was given a particular data set and I had to summarize that data set into two values, let's say the mean and the variance, that the way to maximize the amount of information that I can get about that data using only two values is by using a normal distribution. So that's like honestly, that third point, you don't need to understand, you don't need to know it. It's just, I'm putting it there for kind of anyone that's a bit like, more curious about why the normal is so ubiquitous. And then finally, lots of other distributions have connections to the normal, or they can be approximated by a normal distribution. What I mean by that is basically, let's say you have a some random variable and it's binomially distributed with some n and some p, right? Now, if n, right, if n is large and p is close to 0.5, then your binomial distribution will look like a normal distribution. If n is super large, then it doesn't really matter what p is, your data will still look like a normal distribution. And I'm going to say the word large for the next couple of slides. And large is, yeah, that level of largeness that you need in order for another distribution to be approximated by a normal distribution. That's kind of, that level is determined by various things, and it's usually it's a rule of thumb rather than a hard and fast rule. So for instance, if we have a binomial distribution with 300 trials and a 20% chance of success, then if you plot the PMF, it looks like a normal distribution. It looks like some kind of, normal bell curve, essentially, right? And that's what I mean by an approximation. And this works for other distributions as well, right? We've got the Poisson. If the Poisson's, I can't say that word properly, but if the lambda parameter of this distribution is very large, once again, also large rule of thumb there, then it will also look like a normal distribution. And then there's another distribution that kind of can be approximated by the normal, which is a gamma. And with gamma, remember we have, this is gamma with A and B. And if A is much larger than B, that symbol means much larger, then your distribution will also look like a normal distribution. So that basically is just some of the approximations. You don't really need to know that. It's just extra information that, like, I want to show you to demonstrate that essentially there are lots of connections between distributions and the normal distribution. Now, we need to go over some normal distribution recap so that we can get to our sampling distributions. So the first thing is, this is basically how we write a normal distribution, or this is how we write that a random variable is normally distributed. So that value over there is obviously the mean, and that's the variance. And remember that the standard deviation is equal to the square root of the variance, which is just equal to sigma. Okay, so that's that. Then, oh, sorry about that. I don't know if you can see the kind of, okay, anyway, so that's the PDF. You should know it off by heart, so it doesn't really matter that I've written over it, but that's the PDF of the normal distribution. I say you should know it off by heart, but it's not necessary because, I mean, obviously we will get a formula sheet, but, just learn it because it's important. So that is the PDF, and obviously if you want to get the probability of your x being between a certain, your x random variable being between a certain value, you would integrate this PDF between the two numbers that you need it to be between, or that you want to find the probability of it being between. And then we've also got the moment generating function of the normal. So I just want to quickly point out here, you'll see that I subscript my m. So whenever you see an m of t, that's usually a moment generating function. And you'll see that I subscript this m by this little x over here, or the capital X. And that just means that I'm talking about the moment generating function of this random variable. The reason why I say that, or why I mention that, is because in the proof videos that I do, you'll have a lot of different random variables, running around, and it's important to be able to know what moment generating function refers to what random variable. Anyway, so this is the moment generating function of a normal random variable, and you'll see here that basically It's just a function. So you plug in a value for t and you get another value. The actual value of t, it's known as a dummy variable. So it doesn't really have any significance. Where it does come into play is when you actually want to find the moments of a random variable, then you would have to take the derivative and evaluate at 0. And there's a whole reason for that. I'm not going to go over why that is, but if you want to see an MGF explain a video, let me know in the comments and I'll see what I can do. So, for instance, the reason that I'm going over this is because you need to be able to recognize when you are seeing a normal MGF. And what I mean by that is if I tell you that some random variable h, right, has this moment generating function, you need to be able to basically recognize that, hey, this is of the form e to the mu t plus t sigma squared t squared over 2, right, where mu is this 100 and this sigma squared over 2 is 1125. So essentially you need to be able to say, hey, my mu is equal to 100, and well, I don't really have sigma squared over 2. I just have this number in front of t squared. That's equal to 1125. So that's telling me that my sigma squared, if I move the 2 over to the other side, is 225. So what that means is that h is distributed according to a normal distribution of 100 and a variance of 225. That's important because in a lot of the proofs that you do, or in terms of like figuring out what the sampling distribution is of a particular statistic, you use MGFs and you need to be able to recognize MGFs and where the parameters of an MGF fit in and how they fit into each other and how it relates to the ultimate random variable that you're talking about. Okay, so speaking of MGFs, I said I wouldn't do a lot of explanations, but there are some important facts about MGFs that you need to understand. So firstly, that's just the definition of the MGF. Once again, not going to go into what that means, but there is this important thing. So you'll see here that we have e to the ty, and if we have e of e to the t y and some constant here in front, so this little c value, right, that's equivalent to taking the moment generating function and evaluating it at c. So all you're doing basically is you're taking this t thing over here and you're saying, instead of it being t, right, let's make it ct, or let's make it 2t or a half t or t over n, or anything that you can think of, as long as it's a constant multiplied by it. Then you're evaluating the MGF at a particular value rather than just at t. And the reason that's important is because, once again, it's all about your chapter 6 functions of random variables using the moment of method. Sorry, my computer is making a noise. I'll just quietly make it less noisy. So essentially, sorry, where was I? Yeah, with chapter 6, all of those method of moment generating functions, you do a lot of MGF manipulation, and you need to know what the MGF manipulation is and how it fits into figuring out what the distribution of your random variable is. Then there's this other idea with MGFs, which is basically that if I have, so here I have n random variables, right? If you have these random variables that are independent and identically distributed, so sometimes you'll see this written as IID. That's important because lots of things are well, a lot of the results that we prove or use in statistics kind of depend on IID random variables. But if you have these random variables that are IID and they have a particular MGF, right? And this is the MGF for all of the random variables. That's why I put an I here instead of saying xi. X1 is the moment generating, or has a moment generating function of a particular MGF. I'm just using I to basically mean it's any one of these random variables and they all have the same MGF. So you have these, n random variables, they're all identically distributed and they all have the same MGF. If I take the sum of these random variables. So here I'm going from I is equal to 1 to I is equal to n, right? If I take the sum of all of these random variables, then the MGF of y, right, the MGF of the sum is equal to the product of all the individual MGFs. So this can also be written as MXIT to the power of n. And you use that fact a lot in a lot of the proofs. So this is kind of just recapping MGFs. I didn't really go into much detail, but it's important that you understand all of this. And the reason why it's important that you understand all of this is that in calculating the sampling distributions of statistics, you are basically finding the distribution of a function of a random variable, and that's all chapter 6 things. And in order to find the distribution of a function of a random variable, where either the function is the sum divided by the number, which is the sample mean, that in order to do that, you work with MGFs quite a bit, and that's why understanding all of these concepts are important. So now we're going to get to our first sampling distribution. So we have the sampling distribution of the sample mean. So I just kind of want to go over what the sample mean is. So we have these IID random variables, and they are 1 through to xn. So what this is saying is basically you're assuming, right, that, there we go. Okay, so you're assuming there's this population, right? So this population can be anything. This can be something like, the heights of every single person in second year. This can be the average mark, or the final mark of all of your second year students. This can be the number of car crashes in a particular city in a particular year, right? That's the population. So this is the population, right? Now, each one of these population, every single, I'm going to say, person, if we're talking about heights, for instance, right? Every single person in this population is one particular, is one particular random variable, is one particular xi. And you're saying that xi is normal with some mu and sigma squared, right? So all of these all of the elements, or the people in the population. I'm going to refer to people in the population, but obviously it's not just people. You can think of other examples. But what you're saying is that every single one of the population have exactly the same distribution, which is a normal distribution with one particular mu and one particular sigma squared. And then you go out and you measure these people, right? So it's impossible to go out and measure every single person. So instead, you take a sample. You take an n, right? That's your sample size. Okay. So this is the number of people that you're measuring. This is the number of marks that you're taking. This is, the number of sample points, or the data that you have. Now, I want to reiterate something that I said in the previous video about sampling statistics and observations, and the difference between an observation and a random variable. But basically, these xi's, they are random variables because they could be any value. Basically, there's an uncertainty towards them, or there's an uncertainty that the height can be, or that the mark can be. It can be any range of values, and you don't know what particular value it can be. But once again, I'm going to reiterate, once you go out and you sample, you have taken the measurement, right? You have taken the observation. So you have the observation, which is an outcome, right? This is an outcome. So you no longer have the random variable, you just have the outcome of a random variable. So then what you can go and do is you can go and do all of those descriptive statistics we did in the first semester, in the first week of the first semester, taking sample means, taking sample variances, sample skewness, sample kurtosis, those kinds of things. And you can get a sample mean, right? So your sample mean, xn bar, right, is just the sum of all the xi's from I equaling 1 to n, and then you divide by n, right? That's just the normal average that you're taking, right? And that xn bar is also a random variable. Now, it's a random variable for two reasons. One, it's a random variable because it's a function of random variables, right? Which is always a random variable. But there's kind of this other reason that it's a random variable, which is it's a random variable because the value of our sample mean depends on our sample, right? It depends on who we go and sample. So, for instance, if we sample this portion, right, let's say that's the 10 tallest people in a class, right? That's going to give me a different sample to if I sample here, right? Let's say the 10 shortest people in the class. So, our sample mean has variability or randomness or uncertainty because of the fact that we're sampling and we can get any particular sample depending on how we choose our sample. So that's where a lot of the randomness of a sample mean comes from. It doesn't necessarily come from the actual random variables that it's working with or that it's a sample mean of or a statistic of. And the reason that that's the case is because we have the outcome of those random variables. We don't have those random variables anymore. Anyway, so we have the sample mean xn bar. And this sample mean, as we said before, is a random variable. So if it's a random variable, it must have some distribution, right? It must have some thing that tells us, hey, the probability of being in this particular, so that if this is xn bar, right, it must have some kind of probability or some kind of distribution that tells me, hey, the probability of being xn bar being between these two things, right? It must have some kind of distribution, so it must have some kind of thing that I can take an integral of f of x dx in order to get that probability, right? So because it's a random variable, it has this distribution, and therefore it has all of these nice properties that we can work with. Now, when you go out and you do a sample mean of normally distributed data, the distribution that you get for your sample mean is a very special distribution. It is a normal distribution with a particular mu and a particular variance, right? So this is an important fact. It's basically saying if you go and take normally distributed data and you go and sample it and you take a sample average or a sample mean, the distribution of my sample mean, because remember, the sample mean is a random variable. It can be any value depending on what our sample looks like. That distribution of the sample mean is also normal. Now, that has some implications for later on when we do hypothesis testing and confidence intervals, but ultimately, all this is just saying is that if we want to get the probability of, what is the probability of our xn bar being between sum A and sum B, right? That's just saying, hey, take the integral from, this is B to A, of our density function, which for a normal distribution, we know what it is. I'm just going to put f of x there, dx. So that's why sampling distributions are so important, because we can then use the distribution of our sample mean, right, which is this f of x here, and because it's normal, we know what that f of x is, and we can say, hey, what's the probability of seeing our xn bar being equal to, let's say, 170? So if we have these values, this n and this sigma squared over n, if we have those values, then we can figure out, hey, what's the probability of being in a small interval around 170? So that's the kind of intuition behind why this xn bar being normally distributed is important. I will have a little extra video that goes through the proof of why this is the case. But I do want to quickly, okay, wait, sorry, let me just go back. How do I go back? Here we go. So I want to, sorry, I'm doing this on a tablet so I can draw. I want to just go over this x sigma squared over n thing because it has a meaning beyond just sigma squared over n. It has a meaning to it. So remember, we have this normal distribution, and I'm just going to call this mu, and then we have sigma sigma, and then minus sigma, and we have this kind of idea of, hey, being between these two values is a certain level. But what's important here is that this width that we've got over here, right, tells us that our random variable x in bar, right, this thing can be any value, and essentially we want to figure out, hey, what's the variability? What is the chances of it being between certain points or certain values? And we said that x n bar is normally distributed with a mu and a sigma squared over n, right? Now, I want you to think about like this n value here. Remember, n is the sample size that we have. If we take sigma squared over n, right, and we take the limit as n goes to infinity, right, this n thing over here basically means, because it's at the bottom, right, we're going to have the limit of a constant value divided by something that goes to infinity, which is just equal to 0. So what that's telling us is that essentially, as we take, let's say our n value here is 10, right, and we have some thing like that, right? We have some bell curve that looks like that. As we increase our sample size, right, and then this is obviously mu, our bell curve looks sharper and it's getting less wide. So essentially, we're almost zeroing in to where our mu value needs to be. And the reason that that's important is because, remember, this mu value over here, that's the mu value of our original random variables that we had. So if we have some assumption about what our original mu value should be, then this assumption will fall through into the sample mean, and essentially we can then start looking at, hey, based on this mu value that we assumed our original random variables had, based on the outcome of this sample mean, is that assumption valid? Because the sample mean should be close to this mu value that we assumed we know about the original random variables. And so if our x in bar is like way, way off, and it's like much, much bigger than mu, then something is wrong, basically. Okay. Okay. So why is this important, right? Why is this useful? Well, we've said now that if x n bar is normally distributed, which it is, and I do, hopefully we'll have a video about the proof and you can look at it later, or look at it now and then come back. If x n bar is this particular normal distribution, then remember, we can standardize any normal random variable. So standardizing basically means taking our random variable, right, x n bar, subtracting the mean, and dividing by the standard deviation. So the standard deviation is the square root of the variance, and the variance in this case is sigma squared over n. So this is going to be sigma squared over n, and doing some algebra, you can get that this is equal to sigma and then root n, right? So this over here is some z, where z is normally distributed with the standard normal distribution, which basically means that the mean value is 0 or mu is 0 and sigma squared is 1. Now, right, so we can do this manipulation and we can standardize our x n bar basically. And the reason that that's important is because now we can calculate the probabilities of z, which we know, right? We know what the standard normal distribution is. We've got a table in the back of our book, and basically what that means is, if, for instance, we get an x n bar being equal to 4.5, right? And in our original normally distributed data, we assume that mu is equal to, let's say, 5, and sigma squared is, I don't know, 10, then we can do this xn bar calculation. We can say 4.5 minus 5 divided by, well, the square root of 5 over n, and depending on what our sample size is, we're going to get some particular value, and that's going to be a z value. It's called a z-score. And essentially that just means that we can then say, okay, based on this value, we got, this thing, right? So we got a particular z value. I'm going to call it z0, for instance. That's when we calculate using the values that we know. We know what xn bar is. We assume we know what mu is, and we assume we know what sigma or sigma squared is, and we have n. Then we get this value, this z-score, right? And using our probabilities for standard normals, we can calculate, hey, what's the probability of being close to this thing, or what's the probability of being less than this or more than this, right? So that's essentially what we're doing. And this is just here, we're talking about what's the probability of being in a particular interval. This a value means, hey, I'm between a and negative a, or alternatively, we can do the absolute value of z being greater than a, which just means I'm either here or I'm here. So this is the kind of like overview as to why this is useful, but I want to give you an example now, like a proper example as to how you go about using this. So this is the example, right? Okay, so you are the quality assurance officer of a medical equipment company. The company uses multiple machines to manufacture ventilators, which are used in hospitals around the globe to treat patients with severe respiratory failures. So this is kind of this is a real world example. There are people that are quality assurance officers for medical companies that produce medical equipment. I've just kind of trivialized everything and like made up the numbers, but you can see the importance of why this kind of technique, or this using these tools that we have, why it's important. So the valves inside of a ventilator are of particular importance. They are required to be 50 millimeters in diameter. So this is important, right? This is our requirement, right? Our valves need to be 50 millimeters in diameter. So if, for instance, we have a valve lengths that look like 52 and 57 and 48 and 45, sorry, 45, right? Those are not good enough, right? We need it to be close to 50. And the closeness we need them to be is a question that you would need to answer as, a quality assurance officer. That would be like domain knowledge. But anyway, so we need these valves to be 50 millimeters in diameter. However, the machine which manufactures them has some small error. So this is important. A lot of real world examples, we can't be precisely certain. There's no such thing as a perfect measurement. There's always some kind of small error or an error value that's associated with the measurement. So this small error is basically, in this particular example, it's 0.01 millimeters on each valve. And then, this is important. The machine also manufactures the valve according to a normal distribution. So we now know that the valves that we get out of this machine, right, the diameters are going to be normally distributed. And they're supposed to have a mu of 50 millimeters, right? And a sigma, they have a sigma of 0.001. So their sigma squared will be that value squared, right? Now, shibbit. Let me just try and erase this. Oh, no, that didn't work. Eraser. Okay, nope, that didn't work either. Why is this being so... Okay, there we go. So, right, as part of your job, you have measured... Okay, so as part of your job, you have measured the diameter of 100 random samples that have come off the production line. You calculate the sample mean to be 49.999 millimeters, right? So now you've basically gone out and you've got an xn bar, right? And you've gotten that to be 49.999. Now, remember, xn bar can be any value, really, right? Depending on the sample that you get, depending on what ventilators or what valves you take off the production line. So that's a random variable, and it has this particular distribution, and that's what we derived, or that's what we saw in the last couple of slides. So now, this xn bar, right, you've calculated to be 49.999. If that's the sample mean, right, and it's your decision, it's up to you to decide, okay, am I okay with this 49.999? It's not exactly 50 millimeters, but is it close enough to 50 millimeters that I think that basically the reason I got 49.99 is that it's just due to random chance, right? That I managed to take maybe just 100 of the smaller ventilate or smaller valves that are super below 50 millimeters, but because I took all of the ones that were smaller, my sample mean is below 50 millimeters, right? You need to make the decision, hey, should I let these valves off the production line and into machines to be shipped around the globe? And you need to make sure that you can do that with a clear conscience. So how do you go about doing it? Okay, so this is the information we have, right? We have 100 random samples, okay? The reason I say 100 random sample, 100 random variables is because each of those valves that come off the production line, they have a particular distribution, right? They have a particular uncertainty towards them. They could be 50 millimeters, they could be 50.00000000001, they could be 51, they could be 52, they could be 49, right? And we're assuming that they're normal because that's what the question gave us, and that they're IID, so you'll see that IID little symbol. And so because we have this particular setup, right, we tick the boxes to be able to use all of the information we had earlier. So we're assuming that mu is equal to 50 millimeters. This is what the mean diameter of each valve should be, right? If I'm assuming that they're normally distributed, they have some particular mean, and I need them to be 50 millimeters, this is my assumption that I am making about these random variables. I am assuming that they have this normal distribution, right? Now, and they also have a particular standard deviation, right? So this is the square root of the natural variation which the machine has inherent to its manufacturing process. It's not super important. It just basically means that it's not always going to be 50 millimeters, and there is going to be some kind of difference or deviation from that. But now, what is the standard deviation at 0.01? So because we tick these boxes that we have normally distributed data and they're all IID, we can then use the sampling distribution, right, which is this over here, the sampling distribution of the sample mean, and we can go and do some analysis. We can go and make some inferences, right? So we have xn bar is 100, xn bar is 49.99. So it's quite difficult to think about, some particular normal distribution that looks like this, where the mean value is basically 50, and this standard deviation should be 50.0001 and 49.99 something. It's difficult to think about that distribution and thinking about what the probabilities are associated with that particular distribution. So instead, what we do is we go and standardize it. So that knowing the sampling distribution, we can just calculate the probability of being a certain number of standard deviations away from the mean. That just means we're going to go and standardize it, right? So we take our z value, which is equal to this weird thing. I'm going to call it a weird thing. And we go and plug in the values, right? And now we get a number, negative 100. Now remember, this thing over here, right, this is a normal 0, 1, right? So this is something we kind of have a natural understanding about, hey? There's 0, there's 1, negative 1, there's 1, there's negative 2, there's 2, and we know what the probabilities associated with any particular value is here. So now, if we have negative 100, that's basically saying, hey, we've got a value all the way over here, right? Now, sorry. So if we ask, like we've got a z-score, a z-value of negative 100, what's the chance of getting a value near negative 100? Well, if we have the standard normal where this is 0 and this is 0, 1, we know that basically most of the values are between 3 and -3. So getting a value of -100 is saying, hey, we're like way, way, way in the extremes. Like something is very wrong. So this means that there's something wrong with the production line. Either the machine's not producing incorrectly, or our measurements are off, or the thing that we're using to measure is off. So there's something wrong. So that's why the sampling distribution is important. Because based on our assumptions that we had earlier, right? Based on these assumptions over here, we shouldn't get a z-value of -100. We should get a z-value of maybe like 0.2 or 1 or 0. Or -0. We should get a value close to 0, or between 3 and -3, with a probability of 99.7 or something like that, right? So that's why this whole sampling distribution for the sample mean is important, and why it's useful, because we can use it to make inferences or conclusions about our assumptions, about our models. So we can say, hey, there's something wrong with this production line. Okay, so that was the sample mean. Now we're going to take a detour and go through to the sample variance, but before that, we do need to talk about the chi-squared distribution. Now, the reason we talk about the chi-squared distribution instead of the normal distribution, oh, well, I mean, we still have normally distributed data, but the sample variance, the sampling distribution of the sample variance is not related to a normal distribution, right? So when you go and calculate the sample variance for for normally distributed data, you don't get something that looks normal, you get something that looks like a chi-squared, and that's why we need to do some chi-squared recap. So the chi-squared value, or chi-squared distribution, has one parameter, n, and this is called your degrees of freedom, right? Degrees of freedom, and there's a whole theory behind what this means and how it relates to things, but essentially it's just a number at this point in time. You just need to think of it as being a number for a chi-squared distribution that determines what the distribution will look like and what your probabilities will look like. Okay, so we have this variable v, right? And I'll use different letters, different random variables. You need to kind of get used to that, because the letters that we use to describe random variables is a completely arbitrary choice. So you might see in an exam, the examiner has chosen one particular letter, and you need to be able to understand that the letter doesn't really matter. You just need to know what the letter means. So specifically, this letter is chi-squared. So the chi-squared moment generating function, which is an important function to know and to recognize, is this particular value over here, 1 minus -2t to the power of -n/2. So for instance, if I tell you that one particular h, right, one random variable, the moment generating function is 1 minus 2t to the power of -14, for instance, right? You need to be able to recognize, hey, -14, that's meant to be -n/2. So if I want to calculate what n is, take the -2 to the other side, and I get 28. So this h value over here, this h random variable, is chi-squared with 28 degrees of freedom. Okay, so that's just the moment generating function of a chi-squared. But now we need to think about what the chi-squared's relationship is with the normal. So the chi-squared's relationship with the normal is that if I have some standard normal, right, zi, I use zi just to mean any standard normal, but you'll see why I use i's, because we're going to take a sum of them and you need to index them somehow. So some zi. Remember, the actual letter doesn't really matter. What is important is this, right? If I have a standard normal random variable, okay, right, I have that standard normal, and I square it, right? So I've got this standard normal random variable, and I square it. The distribution of the squared value is going to be a chi-squared with 1 degree of freedom. Now, essentially, there is a proof for that. Hopefully there will be a video little box that you can click on to see that proof, but it's just a result that you need to know. You should be able to prove it. Whether we'll be examined on the proof is a different story, but you should be able to prove it. But ultimately, why this is useful is because if I then go and take, okay, well, that's just saying that what the moment generating function of a squared normal will look like. Because it's a chi-squared with 1 degree of freedom, it will have the moment generating function of a chi-squared where n is equal to 1. But the reason that this is important is because if I have multiple standard normals, right, if I have a sample, for instance, of standard normals, right, then when I sum them all up, that will have a chi-squared of n degrees of freedom. So the n usually is always going to be equal to your sample size when we're talking about statistics, almost always. Sometimes it could be something else, but majority of the time, small n will be your sample size. So if you go and take n random variables that have a standard normal distribution, when you sum them all up, the distribution of the sum of those standard normals will be a chi-squared, where the degrees of freedom is equal to the number of samples that you took. Okay, so that's just the chi-squared recap. I will have videos with proofs of all of these things, but for now you just kind of have to accept them as given. So now we can talk about the second sampling distribution that's important, and that's the sampling distribution of the sample variance. Now, before we get into the actual distribution, I just want to quickly go over what you'll see the sample distribution look like. So, I mean, the sample variance will look like. So your sample variance will usually be denoted by Sn, and this is equal to 1 over n minus 1. And you sum from I is equal to n, where you take your xi and you subtract it from the sample mean. So this is how you calculate a sample variance. You take all of your you take all of your data points and you subtract whatever their sample mean is, and you square it, and then you divide by n minus 1. Please note that you don't divide by n, you divide by n minus 1 for your sample variance. There is a reason for that. Not really going to go into it right now. If you want to know, put something in the comments and I'll maybe mention it. But yeah, that's your sample variance. Now, so this is just if you take these random variables or these samples, right? So this is a sample, this over here, where you have n samples, okay? So that's one particular sample, and all of those values are normally distributed, right, with a particular sigma squared and a particular mu, right? If you go and calculate the sample variance, right, or sorry, this should be s squared or sn squared, s squared, you could call it as well. The n, sometimes you won't see the n, right? I include the n just to show you that it's for a particular sample size. So that's just how you calculate it. Then the sample variance has a distribution that's related to a chi-squared. Now, it's not that the sample variance is a chi-squared by itself. You have to take the sample variance and do something to it, and then you will get a chi-squared. And what you do is you divide by your original variance for each of those random variables, and you multiply by your sample size minus 1. And that has a chi-squared distribution where the degrees of freedom is the sample size minus 1. Once again, we'll hopefully have a proof video that you can click and watch as to why this is the case. It's a very, very long proof, but it's important to know, I think, because it gives you an understanding about it. Whether they will ask it to you in an exam, that's a different question. Whether you want to learn the proof, different question. But essentially, what this means is that if you have some assumption about your sigma squared, so if you have some assumption about what you think your original data, right, what you think the variance of your original data is, if you then go and take a sample of your data, right, and you calculate the sample variance, and you make this little, I'm going to call it a calculation, basically. If you go and calculate it, this random variable, which is a random variable, remember, because it's a function of random variables, if you go and calculated, that will have a distribution, right? A sampling distribution of chi-squared with n minus 1 degrees of freedom. So what that means is that you can then, if I call n minus 1 s squared n over sigma squared, if I call this, for instance, let's say v, right, then I can tell you, hey, what's the probability of my v being less than a certain value or more than a certain value? And you can do it the exact same kind of example that we did earlier with the quality assurance officer. You can do the exact same thing. Usually you would use this for measurement errors to figure out, like, hey, is my measurements actually accurate? What should my measurement error be? What should my standard deviation be for my measurements? And then you go and take a bunch of measurements, and then you'll calculate this sample variance, and then you'll do a calculation with this n minus 1 over sigma squared, and then you can use your chi-squared distribution, which you have the probabilities for, and you can say, hey, was my assumption for my sigma squared, was it a good assumption or was it a bad assumption? And that is the sample variance. And that's the end of this video. Yeah, please like and subscribe, comment if you have any questions, and let me know what you guys want to see next. I will be going through the other two sampling distributions that are in the textbook in another video, and then hopefully going through the central limit theorem. Cool. Thanks, guys. Bye.